Hi everyone, this is Murli Baggu from National Renewable Energy Laboratory and Annabelle Pratt along with me. We'll be co-presenting this specific presentation. Primarily, we'll be focusing on the work that we have done here at NREL on NREL's Advanced Distribution Management System testbed. We have been extensively working with OPAL-RT over the past 3 years to establish this testbed at NREL. I will try to set the stage for this project, and Annabelle will go through some of the use cases that we have been doing and the capability that we have been developing on the specific project. So to provide a little background, the DOE has been the primary sponsor for the ADMS testbed. As you can see, there are a few projects that DOE sponsored as part of the Grid Modernization Laboratory Consortium over the past 3 years. The first one is the platform, which you might be familiar as Grid Apps D platform. The second one, which is this specific project, that's a testbed project. And the thought there is to really develop a vendor agnostic evaluation platform for ADMS applications to really de-risk the technology and test the effectiveness of different applications well in advance. There are 2 more projects. The third one is more application development. Suite of community control algorithms were developed as part of that application. The last one is also primarily going back and looking at control theory approaches that are needed for power systems. So these are the 4 main projects that were funded through Advanced Grid Research Program at Office of Electricity to really take the next generation of advanced distribution management system applications. So they're more open architecture, standard-based data exchange, so that you can integrate them easily with the rest of the legacy applications. This specific project, the ADMS testbed overview, as you can see, is the one that we'll be going through. The main objective of this project is to really develop 3 main things. One is a flexibility to really develop a large-scale distribution system to evaluate ADMS applications. I think this specific task here is to really come up with different tools that we can use on different multitude of data sets to really come up with simple large-scale distribution system models that we can use for evaluation. The second one is we want to really integrate this simulation with real hardware within the energy system integration facility. The figure on the right actually shows a very simplistic view of the 2 items there. One is the simulation on the left, which is the large-scale simulation that we're talking about, which pretty much has the 90% of the network that we're looking at, whereas the 10% of the network, we actually do emulate it in hardware using the power hardware on the loop techniques that we use here at NREL, and I'm sure Annabelle will probably go deep into those. But at the end of the day, the overall box actually shows the 2 simulations together, which we call a co-simulation environment, presented to the upper management system, in this case the ADMS, as a real utility feeder so that they can run different applications or algorithms on this particular test network. Given we'll be using real hardware, we use real protocols to communicate between ADMS and different hardware as well as the simulation. So this particular testbed will actually have realistic communication protocols as it is out in the real world. The third thing which we have been developing over the years is a visualization capability more for this specific testbed to really look at different evaluation data. It's not really a control rule replacement, rather it's more a visualization to look at data that we run through the testbed over a couple of months so that you can look at all the data at one place and really come up with conclusions. We also ventured into some 3-dimensional 3D visualizations in this area, where we actually learned some of those results through the use cases. Next slide. As it says that it's a capability that we're developing here at NREL, the thought is not to just develop the capability as is, but really to look at, anchor it based off some of the use cases, and that's where we came up with the methodology to really identify use cases. I think we are in our use case 3, I should say 4, but the reality there is we have been working with few utilities and vendors together to really come up with different use cases. The way it works is we reach out to utility, or we have some conversations with utility to understand different challenges or define the problem, as you can see the step 1 right there, and also look at vendors to see how they're planning to solve it, or if they are preliminarily deciding to solve it using some of the algorithms, and we define a use case based off these inputs. That's the first and foremost thing we do. In many cases, these algorithms are not fully mature. They are probably going to use the testbed as a means to really develop the algorithms going forward. Once we define the use case, we come up with a test plan, especially looking at what different type of hardware equipment we need, software equipment we need for this specific use case. So the reason we do that is, let's take an example of volt-var control. It might be really targeted towards legacy volt-var devices, at the same time also exercising some of the volt-var capabilities from PV inverters. That decides, okay, we probably need a PV inverter and hardware in the loop, along with probably control in the loop functions of voltage regulators and cap bank controllers. That's the way we look at defining test plan, and also trying to understand how we come up with configuring the test bed. At the same time, we talk with vendors or the ADMS manufacturers to understand how we can communicate with their device so that we can really set up a real-time test bed to test different algorithms going forward. Once we configure the test bed, we actually use the real data from utility, their models, their load data, and actually define the test bed based off of the real utility data. And then we analyze the test plan based on the application that we are looking at. And we provide results both ways to utility, saying that, okay, this is what the benefit you can get out of the specific application. Whereas we also go back to vendors and say, okay, there is a scope for improvement, or I think this does this way for the specific application. We try to give feedback both ways. End of the day, it's actually a neutral environment to test applications, not biased on any direction, trying to understand what different ADMS applications can really do for a specific utility network going forward. Yeah.
So thank you, Murli, for the high-level overview. I will get into some more details that going forward. So the representation here is a bit more detailed than what we showed a few slides back. The essential elements are still the multi-timescale simulation, and we will spend some time on how we set that up. And then the connection with hardware. We can connect both controller hardware, such as protection relays, voltage regulator controllers, etc. We can also connect power hardware through power hardware in the loop. Very common for us here at NREL is a PV or a battery inverter that needs both an AC supply emulating the grid connection and a DC source emulating either PV panels or the battery system. So that's the kind of the simulation and hardware pieces. And then again, the ADMS is what we connect to the system. So our intent is to have our test bed look like the real world to the ADMS. So we will discuss in some more detail how we set up these industry standard interfaces. And even though this program is really focused on ADMS, we also have the ability to connect to other types of management systems. Microgrid controllers or DERMS controller will give some examples where we had both an ADMS and DERMS control. And finally, we also have the ability to connect remotely to other sites. I won't spend much time on this today, but we have a connection with some other national laboratories, and we've also set up a connection with utilities to expand the capabilities of the test bed. And here is a photograph that shows the physical setup. And again, as Murli mentioned, 90% of the network is modeled in simulation. So the heart of it is software simulation that is running, both on the testbed side as well as the ADMS, which is essentially software. We show a user interface here of one of the commercial ADMS systems that we've used. And then here to the right, we show some examples of hardware. We have on the back of this rack, we have a PV inverter. We have some LTC and cap bank controller hardware. I'll talk a little bit later about this Ferentech hardware, and then the supporting PV simulator and grid simulator. And then, of course, the OPAL-RT real-time simulator that we use to simulate part of the network. So for our simulation, based on the use case, we will select an appropriate simulation tool. When we started out, we really wanted to develop the capability to be able to do a multi-timescale simulation. So even though our first use case that I will discuss is around vault-var optimization, that could adequately be simulated with quasi-steady-state time series. Because we wanted to develop this capability, we split that network partly between a QSTS tool. We use the OpenDSS software simulation developed by the Electric Power Research Institute, and part of the network in OPAL-RT. And one of the examples that I'll give, we used ePHASORSIM, and a couple of others we used eMEGASIM on the OPAL side. And ePHASORSIM gives us the advantage of being a dynamic phasor simulation, so we get more fidelity than just the QSTS tool with a smaller time step. And through this project, we partnered with OPAL-RT under this DOE-funded project, and they developed some additional models for us that we needed for our simulation in ePHASORSIM. So this project also expanded the capabilities of ePHASORSIM through the collaboration. So this then was a focus on the simulation tools, and these are coordinated through what we call a testbed coordinator. It is a Python-based software, and it uses the Hierarchical Engine for Large-Scale Infrastructure Cosimulation, or HELICS. This is an open source tool that is developed through a collaborative effort of multiple DOE national laboratories. So I list the website here for those who are interested in pursuing that and looking into those capabilities. And there is continued development on that, so it will continue to mature over the next several years. So that's the heart of it is the simulation, but very important is the communications interfaces. And again, we are aiming to make our test bed look very realistic. So we want the ADMS and other management systems to use their standard communication interfaces that they would use in the field. So we deploy the ADMS at our facility in the same way that it would be deployed in the field. To OpenDSS, we had to develop some new tools because OpenDSS does not natively support communication protocols. So we partnered with EPRI, the Electric Power Research Institute, to provide that interface. With OPAL, we use the licenses available. In the two cases that we discuss here, DNP3 was the communication protocol of choice for the utility. So that is what we used, and used the drivers from OPAL-RT for that. I also want to say a word about the model conversion. As Merle had pointed out, we work with utilities, we represent their system, so we receive their files in the format that they use within their business, which might be Synergy SIM. We had one example of receiving data in a SIM format. So we then have to convert that to the tools that we use in our simulation. NREL has developed this distribution transformation tool that is also open source, and the GitHub site is listed here for those interested. It can take multiple inputs and generate multiple outputs. In our case, we generated an OpenDSS model, and then we perform a validation step comparing the original voltages power flow with our OpenDSS model. And then, as I mentioned, for both of the use cases I'll discuss here, we split the model simulation. So we have another step where we extract part of that OpenDSS model. And here I show the path for one of our projects that we needed an ePHASORSIM model. So we also have a tool available on GitHub for OpenDSS to ePHASORSIM conversion. So these are some of the background steps before simulation that I wanted to point out. So that completes the general overview of the testbed, and now I will go through 3 examples of use cases where we use this testbed. The first one was in partnership with Xcel Energy and Schneider Electric. And the question here, or the request, was to evaluate the performance of the Volt-VAR optimization application for different levels of model quality and measurement density. So the ADMS, and here I have another very high-level representation of our test bed down here. So within the ADMS, there are several typical applications, SCADA and state estimation we use. And in this case, we really focus on the Volt-VAR optimization application. And this relies on a network model. So it is a network-based or a network-aware optimization. And the question is, how sensitive is the performance of VVO to how accurate that model is within the ADMS? So we looked at experiments where we changed the quality of this model within the ADMS and looked at the performance of VVO. There was also a question of whether some of those model inaccuracies could be offset by additional telemetry on the system. So we looked at 2 axes of both model quality and more measurement density on the system, and the trade-off between those. There was a precursor project that did a detailed simulation of 4 different model quality levels and 4 different measured density levels, and that report will be made available by NREL in the near future. On the test bed, we selected a subset of those combinations to simulate. And this is the specific setup that we used in our laboratory. As you can see, just a more specific version of the generic diagram that I showed earlier. So we have our Schneider Electric ADMS with the VVO application, our OpenDSS and ePHASORSIM combined simulation. In this case, the ADMS has control over an LTC, load tap changer, at the feeder head, and it also has control over cat banks on the system to regulate voltage. So we implemented those controllers in hardware, and then we included a PV inverter as power hardware in the loop. And here is the diagram of the feeder. It is about, it's over 3,000 nodes, so it's split fairly equally between OpenDSS and ePHASORSIM. And then the different colored points here are points along the system that we monitored. In this case, we modeled the secondary network as well, so that we could look at secondary voltages. And here are some results to give an idea of the type of results that we have obtained using the testbed. These will be presented at the IEEE T&D conference in a couple of months. So starting with the baseline situation, so this is before the Volt-VAR optimization application is activated, and what we show is the average min and max voltages. So you can see all voltages across the feeder are within the ANSI limits, but they sit fairly high. And in this case, Xcel Energy wanted to pursue conservation voltage reduction. That is how they made the rate case for the ADMS investment to our Public Utility Commission. So we then looked at lowering the voltages for energy savings. The top graph shows the performance if we have a high quality model. So this Q4D1 denotes a high quality model. So the ADMS has a very accurate model within its software of what the actual field network looks like. And then on the bottom, we show that if there is a poorer model quality, then you start seeing some voltage violations because the ADMS now does not have a very accurate model. And in both of these cases, D1 denotes that the ADMS only receives measurements from the feeder head. So it is very dependent on the model quality in this case because it has very limited measurements. We are in the process of running additional experiments where we add more measurement points, and these will also be made available results through technical reports from NREL and papers that we publish at conferences and journals. The second use case that I'll be presenting here is around peak load management. So the question here was to evaluate the performance of peak load management coordinated across an ADMS, a distribution energy management system or DERMS, and an energy management system, an EMS at the transmission level. Here we partnered with Holy Cross Energy, a smaller utility, a cooperative, and they use a surveillance DMS system. So here we will be activating dynamic voltage regulation as the application that surveillance has to reduce voltage and thereby reduce system load. And then it will also use the DERMS, and in this case we do not use a commercial DERMS, but at NREL we have, our colleagues have developed algorithms to manage DERs, so effectively a DERMS. This manages behind the meter assets, so customer-sided PV, EV, electric vehicle, batteries, air conditioner, and water heater is what this DERMS can control, whereas the surveillance ADMS can control legacy devices, voltage regulators, and LTC, load tap changer. Surveillance, much of their cost, operating cost is demand charges. So they have a real interest in reducing peak demand, both through lowering voltage and then through using behind the meter DERs, using batteries to shift load, reducing load through avoiding electric vehicle charging during peak times, etc. So this is an experiment that we are currently setting up. Here is the Holy Cross Energy feeder that we are modeling. It's over 4,000 buses. In this case, we use OpenDSS for most of the feeder and then eMEGASIM for part of the feeder. And this is the part of the feeder where we connect the hardware to the system. And here specifically, the hardware that we're connecting is the voltage regulator controller and LTC controller. This feeder has a fair amount of PV systems already in place. And then what we're also doing is not only modeling the system as it looks today, but Holy Cross Energy is expecting continued growth in rooftop solar and electric vehicles and behind the meter storage. So we adapted the model to reflect a future scenario. And so we have another PV inverter connected through power hardware in the loop. Surveillance ADMS with its dynamic voltage regulation application. Here is NREL's DERMS code. And then another element of this project is that the ADMS and the DERMS will communicate via multi-speak, a protocol that is used widely by smaller utilities. So we partnered with the National Rural Electric Cooperative Association, and we are expanding multi-speak methods to accommodate this need for communication between the ADMS and the DERMS. So this is an ongoing experiment. And then I'll mention just one more. So in this use case too, we had an ADMS and a DERMS. Here we have an ADMS. We use another variation of NREL's DERMS code, But then we also include, Virentech has end-of-line solutions to boost voltage at the end of the line, and coordinators. So these three control systems are all working together. And our setup here is to model, this is also an Excel energy feeder that is split between OpenDSS and OPAL-RT with a Schneider Electric ADMS and NREL's DERMS code and Virentech's GEMS. So a very complex multi-controller setup. And I have just a few results here that I won't be able to go into great detail. The first one is just to show that we simulated a peak PV production time. And here again, there were voltage violations. And by operating the ADMS, the Virentech, and the NREL's DERMS together, those voltages were brought within the limits. And then I will just point out here, you can see the ENGO devices, the hardware. So these were hardware devices that I pointed out earlier in the photograph, that when the set point is higher than the measured voltage, then these ENGOs will produce reactive power to support the voltage. So that concludes our overview of the ADMS testbed and some examples of how we've used it to date. We invite anyone who's interested to get in touch with us, and if there are any other use cases of interest to this community. We thank you for your attention this morning.